Hello everyone. My name is Dr. Marina Minic and I am SPR in chemical pathology and metabolic medicine. I work at Adam Brooks Hospital in Cambridge. I will be talking today about an EQA, and I will go through some basics of EQA in terms of how do we interpret the results, and then also sort of how do we interpret the basic NIQUAS forms, and I'll touch a little bit on the previous presentation that Julia made a few months ago. I'll switch off. As I've mentioned, I'll do a little bit of a EQA recap, definitions and why we do it, and then how the basic NIQUAS EQA report is interpreted. I'll go through a little troubleshooting flow diagram, and then I'll show you some examples to go through when the EQA goes wrong. So I guess when we think about the EQA, the first question we ask is, what is it? Why do we do it? And then how do we do it? And how do we interpret these results? So based on the WHO definition, EQA is a scheme which is provided by an external agency that objectively checks laboratories' performance. So we have an external agency checking how our laboratory works. UCAS defines EQA as running blind samples and then comparing these obtained results with the results of our peers in order to facilitate the ongoing monitoring of reporting accuracy. So EQA provides a measure of accuracy or lack of bias compared to the other laboratories. So the question is, why do we do it? And I think there are two key elements of the EQA. And at the beginning, at the heart of EQA is patient. So for that reason, EQA helps assure us that the results which are produced by the laboratory are accurate and precise, and that the required standards are met to assure us in the quality of the results. On the other hand, EQA also helps us identify the areas for improvement and if a switch to a different method is required. For that reason, EQA acts as an early warning system for systematic errors and detects problems with equipment, with reagents, and in some cases flags the need for review of staff training and competencies. So I'll show this slide on accuracy and precision, and I know you've seen it across multiple presentations over the last few months and weeks, but I think it's also relevant to touch base on accuracy and precision because this is something that is also relevant and applies to EQA equally. So accuracy, as we know, shows how close our measured value is close to the target value, and it shows analytical bias. And numerically or statistically, it's presented as a mean of repeated analysis. And for that reason, it determines if there is a systematic error present. So systematic error is such that it produces a consistent error. And it means that if we reproduce an experiment, we'll get the same answer. So it means that they are predictable and they present in one direction, either positive or negative. And so when we see a systematic error in our assays, that is pointing out that something is wrong with the method, maybe with the reagent or equipment that we are using. So they are predictable errors. On the other hand, precision is a measure of reproducibility and reliability of the analytical method. So the answer we get when we think about precision is, can we repeat a measurement and can we get the same answer? And for that reason, precision is a measure of a random error. It determines if the random error is present. So it's unpredictable and cannot be replicated by repeating the experiment. Numerically, precision is shown as standard deviation and coefficient of variation. And this is important because it does dominate our EQA reports. So unlike the accuracy or systematic errors where we can predict the error and in which direction it might go if the error is not corrected, factors which are causing random errors are unpredictable and they can vary from one measurement to another. So how is EQA done? So the EQA agency sends samples with unknown analyte concentration to all the laboratories which are participating in a particular EQA scheme. Then the receiving laboratory runs these samples as if they were patient samples, and they report the results to the EQA scheme organizers. The EQA scheme organizers then collate the results from all the participants. They perform the statistical analysis and produce a performance report. That report is then sent to each of the participating labs, and then their performance is shown against other laboratories. And then each individual lab reviews their performance, and they're looking if there are any problems, is there any need for any kind of corrective or preventative action. So this is the basic step of any kind of EQA report that we will see. So how do we interpret the NIQAS report? And I particularly focused on this one because I think most of the reports that we see are these. There are obviously other schemes, but I wanted to focus on this one because as a registrar who, sort of when I was faced with these, NIQAS reports were the first ones that I needed to learn how to interpret. So what do we see on this first page? So I think the first thing, and I'll just go through the basics because I think it's relevant, is basically at the top, we will see what kind of assay an analyte is analyzed. And we'll see the number of distribution into which this analysis belongs, and then when was this done. Then we need to pay attention to the type of sample that has been used for analysis, and it's underneath. We usually have 3 samples per each distribution, and in this case, it says that it's a pooled human serum. But then in other cases, these could be spiked samples, or in any case, it will be noted on this side of the graph here. Then next to it, we see the coloring that is used to represent the methods for the histogram analysis. So all methods have this white color, or these are white bars, and then the particular method or method group, they have a different kind of blue shading. And in this case, we only have all methods against this particular Siemens Atelica method. Then in this next bit, we look into the method statistics, and I've put this in a little bit of a larger picture. So we have the total number of methods that were participating in this distribution, and then we have the mean of the results, the standard deviation, and the coefficient of variation. And then for each of the methods that were participating in this distribution, we have the same. The number of participating labs, the mean for that particular method that was used, their standard deviation and coefficient of variation. So for standard deviation, as a reminder, it's important to know that it's a measure how our data are dispersed in relation to the mean. So low or small standard deviation indicates that data are clustered tightly around the mean, and a high or large standard deviation means the data are more spread out. And I guess in this case, we have relatively low standard deviations. On the other hand, coefficient of variation indicates the size of the standard deviation in relation to a mean. So it reflects the precision of the results. The higher the coefficient of variation, the greater the dispersion level around the mean is. So the lower is better. We are looking at the lower coefficient of variation. And for example, here, if not on this particular example, but in general, if our method coefficient of variation is higher than the ALTM coefficient of variation, then it means that our method is very imprecise. In this particular example, if we look at it, the Quidel ortho, so this one here, method has the lowest CV, meaning that of all these methods that are used in this particular analysis and distribution, this result is the one that is most precise. So then we are moving on to the next element of the EQA, and I'll probably spend a bit of time here because it's fairly relevant. So first of all, I'll start with the histogram, and the histogram is a quick visual report of our results, which are compared to other participants. It tells us if our lab results are in consensus with others, and also if we are in consensus with our method. So how does our result compare to our target and to our method group? So now here on this histogram, we see this little arrow, and this arrow tells us where our result sits among other results. So in this case, our result is 526 for vitamin B12, and it sits in this range between 514 and 552. So then this white bar presents the number of participating labs that have reported results in this range, and in this case, it's around 140. And this light shaded blue bar, or part of the bar, presents the number of laboratories which are using the same method like us and who reported the results in that particular range. And so 540 to 552. Result presented by histogram, they normally follow the Gaussian distribution. So the wider the distribution, there's more imprecision. So next part of the graph is this one onto the right. And it's a box which is showing how our EQA result is comparing to the target. So target depends on what is best for a particular analyte. And in this case of vitamin B12, the target is ALTM. But in some other cases, it can be MLTM or GLTM, or results can be compared to the results of a true method. So what is ALTM? ALTM is all laboratory trimmed mean. So it's abbreviation for all laboratory trimmed mean. And it's a statistically trimmed mean of all the results which are provided by all participants for a single analyte or a specimen combination. The ALTM includes data from all of the different methods and kits which are used by all the participants. However, there is something called the Healy trimming, which is used to identify and trim outliers, removing them from the calculations of statistical data such as means and standard deviations. And usually results which are two or three standard deviations outside from the overall laboratory mean, they are usually excluded. So ALTM results are sometimes, or comparison to ALTM values is sometimes difficult to interpret because ALTM is biased to largest user groups and is not always a representation of the most accurate reference or most accurate method or the reference method. And this is because ALTM includes values which are obtained by a number of different methods, which may not always be the most accurate ones, and rarely are the reference methods. And for that reason, as it will be shown in one of the next slides, for some analytes, target value is one which is obtained by using a definite method. MLTM, or method laboratory trimmed mean, is statistically trimmed mean of all the results which are provided by all participants using the same method principle. For example, if we have a creatinine assay, it would be all users of enzymatic method versus all users of Jaffe method. And then group laboratory trimmed mean is similar to MLTM, but includes results from laboratories which are using related methods within predefined groups. To go back to comparisons, we have our result and we have the target value. So specimen bias, which is here, obviously you've seen that before, tells us how many percent our results is away from the target and in which direction, whether it's positive or negative. It's calculated using this particular formula here, and then interpreted using the RAG, or red, amber, green traffic light system. Here, red means unacceptable bias, amber means acceptable but borderline bias, and green means acceptable bias. For our particular case, the bias is only 2.3%, and it's acceptable. Then the accuracy index is calculated. It is a transformed percentage bias with sign removed, and it's comparable between all analytes. And it's used for calculation of A score, and I'll come to that in one of the next slides. So this is just a slide to show a different kind of comparison to ALTM. So here we have vitamin D, which comes all from pooled human serums. The target, our result is compared to the target value, which is obtained by mass spectrometry, which in this case is considered a definite method. So the ABC score, and this is something that we all sort of used to interpreting when we look into our EQA results. So ABC scores are based on statistical analysis of results which are obtained over a period of time, which is called the rolling time window. It combines data from a wide range of specimens that were analyzed from recent sample distributions. They give an indication of our lab's average performance over time, and rolling time window is usually set to cover 6 distributions or 6 months, and has 18 data points because each distribution has 3 samples to analyze. There is also a RAG system used, in traffic light system used for interpretation. And here for this particular example of vitamin B, we can see that our A score is acceptable, that both B score is also acceptable, and C score is borderline, showing a borderline performance, which means that, and also here we are using a system of errors is used. This particular errors means that the performance in this distribution has been stable compared to the previous ones. However, if we have this different kind of downward going or upward going errors, it means that performance is getting worse or performance is getting better compared to the previous one. So now to go to the A score, and what is this? So it refers to the accuracy of our method, and it represents the total error, and it tells us on average how good our performance is. As I said previously, it's calculated from the specimen percentage bias, and it's transformed by using a degree of difficulty factor. And being a transformed number, A score is comparable across different analytes. The lower the A score, the better, and scores between 0 and 100 are considered acceptable. 100 to 200 are borderline, and those above 200 show unacceptable performance. Unlike A score, which is comparable across the analytes, B and C scores are not. So B score tells us how far away from the target our lab is for the concentration of the analyte. And it's a trimmed mean of the individual specimen percentage biases in the rolling time window. So depending on the analyte, the range of acceptable B score is going to vary. So in this case, for example, for vitamin B, the acceptable variation in the B score is plus minus 20%. However, if we have sodium, this acceptable percentage of variation is going to be much lower. For example, it's going to be tighter, plus minus 5%. And this is due to the clinical implication of that the higher bias may have on sodium result interpretation for the patient. Finally, C score refers to the consistency of bias and tells us how variable our lab's bias has been during the rolling time window period. The lower the C score, the better. And same applies for the B-score. The lower, the better. Statistically, the C-score is trimmed standard deviation of the individual specimen percentage biases in the rolling time window. Here, it's this page is a snapshot of one's laboratory performance, which is described across a range of graphs. So the right-hand side of the graph shows trends which are over the past 1 year, and luckily here we have distribution 301 to 312 to show that this has been over a period of 1 year, and we can see how the A-score has changed over this period of time from being borderline acceptable to now being acceptable. And then same is for the B and C scores. So the extreme right, or actually, yes, extreme right data point. So these here data points, and I'll focus now on the A score. For the A score is a synthesis of all specimen accuracy indices, which is last 6 distributions. And given that there are 3 samples per distribution, this is a synthesis of 18 data points. So each data point is shown individually on the left-hand side of the graph. And so on the other hand, when we go to the B score, the extreme right-hand data point is the B score, which is the average of 18 individual specimen percentage biases, which are shown on the graph on the left. And when we go to the C scores, again, the extreme point on the right is the standard deviation you get when you put these 18 percentage biases into the calculation of the B scores. So the trend reflects the historical data over a period of time. So I've put the analysis, or I've shown this slide with a seismograph plot analysis because it dominates pretty much all the interpretation of our data when we analyze, and it gives us a good chronology of how our assay has been behaving over the time. So it shows a trend, a B-score trend over a period of 5 years actually here. So it includes the data which are specifically related to the method that our lab is registered for, or any lab is registered for. In this particular case is the estradiol, analyte is estradiol, and the method is Siemens Advia Centaur. So the seismograph plot shows box and whisker data. So these malls are called box and whisker data for the B-score of method data over the previous 5 years, as I said. And on the x-axis is time, and on the y-axis is the B-score is shown. The individual box and whisker plot for each distribution, so are shown here. So the box comprises the 50% of the data from 25th to the 75th centile, and the bar represents the median. So the whiskers, they show the 5th and the 95th centile for the B-score, and the individual B-score for our lab is shown by the colored points. So it shows the level of bias, whether it's acceptable, borderline, or unacceptable. So it's actually, the seismograph is a very good tool to review the overall method performance over a period of time and how our lab is performing compared to other methods over time. So in this particular example, we can see that this seismograph allows us to identify changes in performance in the laboratory or changes within the method. And as we can pick up here, we can see that there's been an acceptable variation over a period of many years. However, over the past 13 distribution, this performance became more positively biased, and and it slipped to amber from this distribution here, which I think is 487. As all users of this method have been positively biased, this result probably suggests that there's an issue with the method, or there's an issue with the reagent or calibrator that is used across different labs for this particular analyte. The next one is the penalty box plot analysis, and I think it's also relevant to know because gives us sort of where our method stands compared to other users of the same method and other users of different methods. So the penalty box plot is a plot of a B-score, which is shown on a y-axis, and C-score, which is shown on the x-axis. Again, the 5th and the 19th centile of B and C score for our method are contained in this shaded area, whilst the overall 5th and the 95th centile are contained within the white box, which in this case is quite wide. The limits of acceptable performance for B and C score are shown by these dashed lines, and the best place to be is to be close to 0. So we want to have 0, the B score closer to the 0 as possible, and also C score close to the 0 as possible, which in this case, I would say it's actually quite good, and it's almost ideal because we have a very low B and C scores. So the X shows our lab method. The little circles are showing all other users of the same method. And as I said, the white box is the overall method users. So as I said, in this case, we have an example of a female testosterone with a very good B and C scores. Okay, so if we have poor performance on EQA, so now we have the basics for the interpretation of the graphs, what do we do next? And how do we interpret the data? So I guess the problems can be divided into bigger groups. And this is how I was always taught to think in these terms as pre-analytical, analytical, post-analytical. When we think about the pre-analytical issues causing EQA problems, they are usually related to EQA samples. So this can be delay in delivery or analysis of the sample. It can be the problem with reconstitution, or sometimes the sample can be reconstituted and then left to sit before it's analyzed. Or it can be due to storage condition, where the sample is received but then inappropriately stored before it's analyzed. Most commonly, we actually see analytical errors, and I'll talk about them in a little bit more detail. But depending on the on the direction and frequency of these errors, they can be either systematic or they can be random. And then finally, we have post-analytical errors, which are usually due to some kind of a transcription error, or it can be due to some kind of a calculation error, or, for example, when the wrong units are used for reporting. And they are usually the easy ones to spot because the biases, they get quite large. So when we think about the analytical problems and the systematic and random errors, the systematic errors are the ones which are seen as a shift or a drift. And it's something that, for example, if we go back to this slide, we can see here, we can see this shift towards showing a positive bias, which is suggestive of a systematic error. So when we see something like this, there are a few things to think about. So is it change? Have we experienced the change in reagent or calibrator lot number? Have the reagents that are used close to the expiry date, or have they passed the expiry date? Or have they been contaminated? Has there been a calibration error when the instrument was calibrated? Can we see the calibration curves? Can they compare well? Are the values correct? Or have we missed the calibration? Or do we need to calibrate the instrument more frequently than we are doing it currently? Then another issue is instrument maintenance. So If the systematic error has happened, we ask a question: has the instrument gone planned or unplanned maintenance? Has there been any change of parts? Do we need to do an extra clean? So these are the things that should be flagged when we see this kind of a shift or a drift. On the other hand, random errors are usually, as we call them in precision, or flyers. So I guess flyer is a one-off unexpected result. Or we can see that imprecision is increasing from one distribution to another. The fly is frequent. Is precision better on another line? Do we again have instrument issues? Do we have blocked probes? Do we have problems with tubing? Do we have contamination, misalignment? So these are all the issues that can cause this kind of random error or a flyer or imprecision. So I made this diagram. I try to make it as simple as possible. So I've started with post-analytical issues because they are very easy to spot. So if we have a post-analytical issue, then we go, we rectify it, and then we say what actions can be taken to resolve this error and prevent reoccurrence. And in this case, it's usually either IT issue or it can be a human error, possibly if it's a transcription error in case. So then we move on to the analytical causes. And again, we look into the results and we think, is this a systematic error or it's a random error? And we ask the relevant questions. Depending on whether it's one or the other, we ask the question, can we correct whatever we've noted, whether it's an issue with IQC or reagent lot calibration, is it a flyer or something? We correct it, and then we repeat the EQA, and then we ask a question, is the performance now acceptable? So if the performance is not acceptable, then we undertake further investigation, and we usually have to call the engineer. And once the problem is resolved, then we again summarize everything and think about how to prevent it happening in the future. If the analytical cause is not the cause of the error, then we are left with the pre-analytical causes, which again takes us back to EQA integrity. And we need to think, when the sample was delivered, was it stored properly? Has it been reconstituted properly? And what has happened between the receiving of the EQA sample and its analysis? And again, when we've identified issues, we make the investigation, root cause analysis, and then we learn from it. So I'll now show a few examples from our lab where the EQA has gone wrong. And these examples are chosen to illustrate the transcription or post-analytical, analytical, and the pre-analytical issues with the EQA samples that have led to the abnormal EQA result. So for example, here we have 3 samples for ethanol, which are at different concentrations, so higher, lower concentration, and the medium concentration. And we can see that a negative bias for at the high range of the assay. However, for the mid-range of the assay, we can see that there's been a really high bias, 300% positive bias, which is quite unusual because the target was 4.9 and our result was 20.9. So in this case, when we see a result like this in the EQA meeting, the first thing we do is raise a non-compliance and investigate it. And in this particular case, the investigation showed that the wrong units were used for submission. So the transcription error was rectified and then submitted to the UCAS. So this was a simple case of a transcription, of the post-analytical error that has caused such a huge bias. This one was a little bit more complicated. So this one is to illustrate an analytical issue. And in our lab, we use Siemens method, Siemens Italica, to run sodium or to measure sodium. We have 3 lines. And for the purpose of this presentation, I've used the results from the 2 lines. And as we can see here, across several distribution in line 1, we have acceptable positive bias from this distribution 1148 to the 1158. However, if we look into the line 2, we see that something has happened here, because from the distribution 148, we've noted a positive bias, which is shifting and going now to be borderline acceptable. And this has got worsened over the time and continues to persist throughout the next 6 months. Okay, so what we've done? So we've done done the non-conformance report and started the investigation. So all the samples have been rerun on both lines, and similar results were obtained as in the first run. So then we look into the IQC and check it and see if the IQC is showing any problems on the day when the samples were run for the first time, but also when the samples were repeated. And there were no issues reported, which then suggests that there is an issue with particular line 2. So further analysis of calibration data demonstrated that the IC module that is required, that is used for this particular method, ion selective electrode module, required cleaning when the chip was changed, and that has not happened. And because the chip was changed, but the cleaning was not performed, this has led to this positive bias. So when this issue was identified, the main action that has followed was that that operators of the instrument, they need to be reminded to perform the advanced clean before every chip change, and that replacement of the chip must not be approved in order before the clean is due. So when this change has been rectified, we can see, or spotted and rectified, we can see the improvement in the distribution. And when the issue was finally resolved, we can see that we are going back now to the acceptable range for the bias in distribution 1161. And this slide here, which I've skipped, and I'll go back to it, is showing the B and C box plots for the line 1 and for the line 2. And we can see that across these distributions, our method is performing well for the line 1, and we are in the middle, and on this end there is a bit of a shift, but we are still staying within the acceptance limits, and it's same for the later distribution, some 10 distributions later. However, for the line 2, we can see that when the issue was resolved, we are within the acceptance limit. However, when as the issue was persisting, we can see that our method or our lab is outside of our method group, and also overall method, which is implying that the problem has been persisting, and it requires action and resolution. So this is another analytical issue that I wanted to present, and this is something that probably some of you who are using Siemens Italica method for cortisol have come across. So in 2023, there has been a change in method for the Italica Siemens cortisol users. So what has happened here is that the, you can see here, this first slide shows our lab and where it sits within the overall cortisol method. And we can see the trend of the B-score, which is showing the old method. So we are still within, there is some positive bias, but it's green and it's acceptable. So few distributions later, we have a change in method. And this has been from the distribution 507, where we started noting a bit more prominent positive bias. So before the introduction of the new method, the manufacturer introduced us or informed us that the new method will be introduced shortly, that based on their investigations, the method comparisons, the old and the new method compare well, and that based on their studies, no bias was noted. However, as I mentioned, by this point here, distributions 508 and particularly 510, we've noted the significant bias, which was in the range of 30 to 35%. In this case, practically, if we look at the box plot, we can see that all the users of this method, in particular, and our lab in particular, is actually is very much outside of the acceptance limits, and it's the very sort of end of acceptance for this particular method. So this problem has persisted over time, and the more users were using the method, the similar has been observed. And I guess in this case, it's a clinical impact of the significant positive bias in cortisol results, and this required further investigations. So we've done our method comparison studies in our lab, and we've shown a positive bias, not only with the EQA samples, but also with patient samples. And given that the problem was noticeable not only with the EQA, but also with patients, it implied that it's more likely to be the problem with the method rather than the EQA or similar. And therefore, the manufacturer was contacted, and this was brought to their attention. As the new method was sort of rolling out through other labs, other users of the same methods around the world were also reporting the same positive bias. Our in-house studies by the distribution of 522 have shown that there is also a difference in the level of bias between male and female samples, and we brought this to the attention of Siemens. And we've been reassured that the fix is being made and hopefully will be in place by April 2025. The question is, what is the main implication of this significant positive bias? And how does it reflect on the cortisol result reporting, both in random cortisol assay, but also in dynamic function tests, including short synaptin test and dexamethasone test? When it comes to, for example, dexamethasone suppression test, if you have a significant positive bias, it means that some of the patients that would normally pass the test and have the results below the threshold would now be reported as a positive dexamethasone suppression test, which requires then additional testing to rule out the the abnormal result, because the dexamethasone suppression test is used in when we are trying to identify the cases of cortisol overproduction or Cushing disease. So I guess in these cases, it's very important to inform the endocrine team who is receiving these results and interpreting these results, keeping them informed about the method, about the bias, and in some cases, a different temporary reference range can be adopted to take into account a positive bias such as this one. And finally, I have one more case to show you, which shows the pre-analytical issue. And this is a request report again for as a case would be for ethanol. So in this case, we have the white bars. They show all method users. The green bars are the ones which are using the enzymatic kinetic assay, and the blue ones are the ones who are using the Siemens Atellica solution. And we can see that the mean of comparison here is 33.98, so that's the target that we are aiming for. However, our result is showing a significant negative bias, as our result is only 22 and is shown by this error. Again, in this case, the non-conformance was reported, and the question was asked: why do we see this significant negative bias? And in this case, it was shown that calibration was fine; there were no issues, as well as the IQC results on the day. However, further investigation revealed that the sample has been reconstituted the day before and then just left to sit, and then it was run the day after. So in this case, the sample instability is the cause of this significant negative bias. So the sample was taken again, rerun, and then the result was more closer to the mean for comparison. So these would be the examples that I've prepared for you. And finally, I hope that with this presentation, I've managed to demonstrate why the EQA is required, and why it's necessary to objectively check one's laboratory performance. It gives us as a laboratory, but also our users, confidence that the results which we produce are accurate and precise. I hope I've demonstrated that this poor performance can be caused by a range of issues, from pre-analytical, analytical, and post-analytical, and that we have to be quite systematic in investigating the cause of the error. And that if we have these sort of this flow diagram somehow in place, it will be much easier to troubleshoot and come to the cause of the poor performance result that can be then rectified. And finally, I would like to acknowledge Ms. Cassie Dix and Sue Oddy, who are brilliant clinical scientists in our lab, and who kindly helped me find these examples to present in today's presentation. So I thank you, all of you, and I thank to the organizers for allowing me to present today and share this with you. Thank you.